Yeah, students, welcome back to next session where we are going to complete the components of vapor compression refrigeration system. We have discussed the compressors first and then condensers, evaporators. Now we are going to see the throttling devices, or it is also known as expansion devices. So this is the last topic in second unit. So we are completing unit 2 here with this session, and we will move on to third unit where vapor absorption refrigeration system. So that we will see in third unit, and that will be similar to vapor compression only. I will tell you the significant differences, and we will deal the vapor absorption refrigeration systems in detail. So here these are all the topics we have seen so far, and we are ending the expansion devices today. We are obviously ending the unit 2 today. So expansion devices, the refrigeration system operates in a closed cycle that repeats itself. So it is a closed cycle, it is a repetitive process. There are two pressure sides in the system. One is high pressure side, so between compressor and expansion device, where pressure and temperatures are high. So between compressor and expansion side, we have high pressure side, and a low pressure side where the pressure and temperature are low to maintain proper refrigeration. So low pressure side is where pressure and temperature both are lower. So function of the expansion device here in a refrigeration system is the compressor increases the temperature and pressure of the refrigerant. The expansion device, also called as metering device, it is also known as metering device, is responsible for reducing the pressure of the liquid refrigerant, reducing the flow of refrigerant of the evaporator. So working of the expansion device, it feeds the proper amount of refrigerant to the evaporator. So amount of refrigerant that goes to evaporator is actually sent by this expansion valve, or it is also metering device. The refrigerant entering the expansion device is high temperature, high pressure subcooled liquid, and the refrigerant leaving the expansion device is low temperature, low pressure saturated liquid. So now this change is happening. So from high temperature, high pressure subcooled liquid to and low temperature, low pressure saturated liquid. So this change is occurring here. The saturated liquid consists of 80% liquid and 20% of vapor. Since the refrigerant is saturated, there exists a pressure temperature relationship. So types of expansion devices: thermostatic expansion valve, automatic constant pressure expansion valve, low side float valve, high side float valve, capillary tube, hand expansion valve. So these are the 6 types of expansion devices used widely, and we'll see one by one. So first one is thermostatic expansion valve. So here the working principle is very simple. The thermostatic expansion valve ensures constant superheat in refrigerant vapor leaving the evaporator. So that is the working principle. The valve controls liquid refrigerant flow to maintain the correct amount of refrigerant in the evaporator. So and also it take care of the quantity that is to be supplied to evaporator. It differs from capillary tube, which does not modulate the fluid flow. So there won't be any change in fluid flow like in capillary tube. So that we will discuss in this session itself. The valve consists of power element that is activated by remote thermal bulb. So function of thermal bulb here is the thermal bulb is located at the outlet of evaporator coils. So it contains a power fluid. So it senses the superheat at the suction line and adjusts the refrigerant flow. So I will show you the figure. So here this is the thermostatic valve. Already we have seen this in earlier session also. So this is the expansion valve, and it is connected to evaporator, and this expansion valve takes care of how much quantity to be supplied to the evaporator. And this is the thermal bulb is placed here, and this is the thermal bulb in thermostatic expansion valve. So operation of thermostatic expansion valve: when there is excess refrigerant load and superheat increases at the evaporator outlet, so this causes a rise in temperature in the remote bulb, and as a result bulb pressure increases. So increased bulb pressure forces the diaphragm downward, opening the valve. So this admits additional refrigerant into the evaporator. The additional refrigerant has three effects. It provides more refrigerant to absorb heat from the evaporator and applies a higher pressure to the diaphragm, forcing it upwards to close the valve, and it reduces the degree of superheat due to more refrigerant availability. So thermostatic expansion valve, it is TX valve mechanism. So components and the pressure mechanism: the needle and seat assembly in the valve is controlled by three pressures: evaporator pressure PE, and the spring pressure PS, bulb pressure P beta, and these pressures act on the diaphragm. So which positions the needle in the valve seat. So evaporator pressure, it helps to close the valve, tries to push the needle into the seat to reduce refrigerant flow, so it controls the refrigerant flow. The evaporator pressure is measured from either inlet, either the inlet or outlet of the coil. If the pressure drop is marginal, the inlet and outlet pressure are closed are closed, and internally equalized TEV, so that is thermostatic expansion valve measures inlet pressure. Externally equalized TEV, it measures outlet pressure. So spring pressure is determines superheat in the evaporator. Higher spring pressure, there will be higher superheat. So the factory set is should only be adjusted by trained professionals. We cannot adjust this. We should not do as unknown person, and we should it should be done by trained people only. Improper adjustment can cause compressor failure. So that is the major failure may occur. And bulb pressure, only pressure that opens the valve, so it is responsible to open the valve and generates inside the thermal bulb located at the evaporator outlet. So higher bulb pressure, more refrigerant flow. So this is the complete picture here, and you can see the bulb pressure acts here. This is the diaphragm, and it is connected to spring, and it is the connection from the condenser. So this is the thermostatic expansion valve, and the spring pressure acts here due to the spring fitted here, and we can adjust the screw, but it should be done by the proper trained people. So on the diaphragm you can see here the PE and PS acting here, and PE is acting on the top. So that is the bulb pressure. PB is acting on the top. So these are the three pressures acting on the diaphragm, and it is connected to evaporator, and this side it is connected to the remote bulb. Remote bulb is placed here, and from evaporator the refrigerant comes, and it gives to evaporator the proper amount. The from condenser it receives, and it gives to evaporator coil in terms of metered quantity. So externally equalized thermostatic expansion valve. The externally equalized thermostatic expansion valve is used when the pressure drop across the evaporator coil is large. So in this case, it is widely used. In such cases, measuring the pressure at the inlet of the coil may not accurately reflect the conditions at the outlet. When the pressure drop occurs, the drop crosses the coil is smaller that is lesser than 2 psi or 13.8 kilopascal, an internally equalized valve is preferred. So in this case, the internally equalized valve is used, as it eliminates extra piping connections and could lead to refrigerant leaks. So operation of externally equalized thermostatic expansion valve are at different temperatures. The thermostatic expansion valve can operate over a wide range of evaporator temperatures. And example, a low temperature system must control refrigerant flow at both design temperature and during pull down operation. From pressure temperature characteristics, a pressure difference of 100 kPa between power fluid and evaporator pressure requires 5, 5 Kelvin superheat at 5 degrees Celsius evaporator temperature and 12 Kelvin superheat at minus 30 degrees Celsius evaporator temperature. At low temperatures, a large portion of the evaporator becomes ineffective due to the greater superheat requirements. So decreasing the superheat setting may help, but it could cause liquid floating in the compressor and leading to temperature pull down issues. So this is another drawback. So solution to low temperature operation: use a valve with a cross charge. So the power fluid inside the thermostatic expansion valve is different from the refrigerant in the system. The power fluid is chosen to ensure that superheat required to open the valve remains nearly constant across different operating conditions. So automatic expansion valve. So we can have an automatic expansion valve also. So this is the diagram. So this is automatic expansion valve, and here a pressure reducing expansion valve. And the working principle is very simple. The automated the actuated by evaporator pressure itself. So evaporator pressure is acting on this. So that's how it acts automatically, and maintains a constant evaporator pressure which keeps the refrigerant temperature stable. So here this is the adjusting screw. So in reverse direction I am showing here, and this is the diaphragm and the valve inlet and liquid in, and the evaporator pressure also maintained here. The evaporator pressure is also taken into consideration here, that keeps the automatic expansion valve, and that how it works, the automatic function. Unlike a capillary tube, it opens and closes to regulate the flow of refrigerant. So automatic expansion valve operation is very simple. Uses a needle and seat mechanism only. So by keeping in a reversal direction, right, we can have this arrangement. The position of the needle is determined by the difference between spring pressure and evaporator pressure. So spring pressure is the opening pressure of the valve, and evaporator pressure is the closing force. And spring for pressure preset to desired evaporator pressure. Higher spring pressure, higher evaporator pressures. Evaporator pressure closes the valve when refrigerant evaporates and pressure rises. Uses a diaphragm or bellows operated valve. So evaporator pressure acts on one side and the spring pressure acts on the other side. As compressor removes refrigerant, evaporator pressure drops. So more refrigerant enters, evaporator pressure increases, and now it forces the diaphragm to close the valve. So this is the diagram, and these are the float valves. So float valves. So evaporator is kept here, and condenser is here, and this is the float ball. So this is the float ball, and this acts as the float valve, and this is another another method, float valve. So liquid refrigerant is from evaporator, from throttle, that is float valve, is sent to evaporator. So it receives from condenser, and this is operated or controlled by float. So this is the regulate refrigerant flow based on the liquid level, and two types: high side float valve, low side float valve. And the high side float expansion valve, it is similar components of low side float valve, and hollow ball linkages and needle valve are kept here, located in a liquid receiver in an auxiliary container on the high side pressure of the liquid of the system. On float valves functioning, the condensed refrigerant from the condenser enters the valve. The valve immediately opens to release the refrigerant into the evaporator. It prevents uncondensed vapor from the passing through, and the importance of this proper charge is overcharge results in floods the evaporator and damages the compressor. So that is the disadvantage. And undercharge also causes and reduces the system capacity, and it acts directly on system capacity. And application of float valves used in small domestic commercial refrigeration systems and a single compressor type or expansion evaporator and condenser type. So with this, right, it is used in small domestic and commercial refrigeration systems where it is a smaller capacity system. So low side float expansion valves, it controls refrigerant flow rate and maintains liquid level in the evaporator. So functioning here is it uses a ball float housed in a chamber or inside the evaporator or low pressure side. So as refrigerant evaporates, the liquid level drops, lowering the float. So the linkage mechanism opens the valve, admitting the more refrigerant. As the liquid refrigerant rises, the float lifts, so then it closes the valve. So provides precise control of refrigerant flow, ensuring proper liquid level maintenance. So functions well irrespective of load changes. So compressor off cycles are varying conditions. So multiple evaporators can be used in one system, with each float valve controlling its individual evaporator. So the next one is capillary tube. So capillary tube is another mechanism, and you can see this is the fixed R phase expansion device used in small refrigeration and air conditioning systems. And you can see here, this is the condenser, and the capillary tube here here is fixed during with the suction line for heat exchange. So this is the capillary tube is placed between evaporator and compressor. So this is capillary tube, and this also regulates the refrigerant to the evaporator. And a fixed R phase expansion device, it is as simple as this. It is a fixed R phase expansion device only, and it consists of length of small diameter tubing 1 to 6 meters long, 0.5 to 2 millimeter inside diameter. So inside diameter is very small. You can see here it is 0.5 to 2 millimeters only. It is very small orifice. It is just orifice diameter is 0.5 to 2 mm, located before the evaporator. Works on pressure drop principles, and as the refrigerant flows through friction and acceleration cause a drop in pressure, some refrigerant flashes into vapor, further reducing pressure. So advantages of capillary tube is eliminates receiver tanks, reducing refrigerant charge, and simple construction, fewer moving parts. So only one R phase fixed R phase expansion device is required. So challenges here: no active modulation of refrigerant flow, leading to inefficiencies under varying loads. So that is the biggest challenge, and requires an accumulator to prevent flooding to liquid refrigerant into the compressor. So I will show you one diagram where the capillary tube entwined entwined here with the suction line. So it is placed with suction line, allowing heat exchange, shows refrigerant flow. So metered liquid refrigerant enters the evaporator coil. Refrigerator refrigerant vapor exits the evaporator. So this is the small arrangement. So here the liquid refrigerant from condenser entering the capillary tube. So this is the capillary tube with orifice. The metered liquid refrigerant leaving the capillary tube and entering the evaporator coil. So the refrigerant vapor leaves the evaporator. So this is the capillary tube used as this. So selection of capillary tube, the tube bore and length must be carefully selected to ensure the system reaches a balance point at the desired operating temperature. The key considerations: the longer tube, higher pressure drop, and the shorter tube, less pressure drop. So it is obvious when the longer tube is used, a higher pressure drop will take place. And replacement tubes must match the exact specifications. And a large bore capillary tube requires greater length to achieve the same pressure drop. A smaller bore tube must be shorter to maintain correct operation. So hand expansion valve. So this is the last type of expansion valve. A manual valve. It is a manual valve used for refrigerant flow regulation. So there are two types: needle seat. It is a smaller size, and a plug type tapered seat. So that is large size. So advantages of this is small, simple in construction, low cost, reliable, and minimal chances of failure. Disadvantages are requires manual adjustment. Operator must be available to adjust settings for changing loads. So use of this hand expansion valves, it is typically used in large systems as bypass valve around automatic control valve. So this is one use. Another use is it allows operation during repairs or automatic valve failure. So it is also very handy when the valve failure occurs. So there the expansion valves we are completing here. And students, now with this we have completed the unit number 2, and as I have prepared one more comparison, students, expansion valves, and I have compared all the valves and I have made this table. I have included in the notes also, right? Please go through these differences, and this table I have prepared, and by comparing all the expansion valves, that is thermostatic expansion valve, automatic expansion valve, high side float valve, low side float valve, capillary tube, and hand expansion valve in terms of control mechanism, primary function, and its applications. So these are the three factors I have taken into account to compare these valves. So here the superheat based control mechanism, and these are the control mechanisms I have listed here, and please read these once. It will be more clear and easily you can remember all these 6 types of valves very easily, and you can write in our own words in exam. And diagrams also you can practice, and where you can easily explain the diagrams. There completes our syllabus for unit 2. In next session, students, we are going to start unit 3, and please refer these books. These are the references, and I say thank you here, and we are completing unit 2. We will meet again in unit 4 in next session. Thank you students.